But I think it's about time that I introduce today's speaker, which is Bobak Kiani. Bobak is a person that I know from my time at MIT. He's a PhD student of Seth Lloyd's, and during the last kind of couple of years, he's been very productive in proving very cool results in quantum machine learning and quantum neural networks. So I'm really looking forward to this talk. I think with that, I'm going to hand over the virtual floor to you, Bobak. Thanks for coming.
Yeah, thank you for the introduction, and thank you everyone for attending this talk. I'm very happy to be giving it and sharing this work with you. Let me try to share my screen. Let me know if everyone can see what I see. Just a thumbs up.
Yeah, this looks like it's working.
Okay, great. So today I wanted to talk with everyone about a recent paper we put on the arXiv about using an earth mover's distance for quantum machine learning. I know some of these words may be unfamiliar to you, so I will go slow. I know I've been told that not everyone here is in the field of machine learning. So I've intended this talk to be for a general purpose audience. And if you have any questions, please interrupt me and ask. Okay, so our agenda today is I'm going to first review some of the status of machine learning in the quantum realm. What are the challenges, and what do we need to do to improve the field? And then I'm going to introduce the earth mover's distance, both classically and the quantum earth mover's distance. This is also called the Wasserstein distance. For some of you may be familiar, but I'll go over all these definitions and discuss why we actually want to use this earth mover's distance. And then we'll go over what we did in the paper, which is use this distance to construct a machine learning algorithm in the quantum realm that allows one to learn a quantum state. So let's say you have some quantum data that's encoded in some quantum state. You want to learn how to generate that data, how to get close to that quantum state. Then you can use this, what we call Wasserstein generative adversarial network to do that. And the final thing we'll do is we'll discuss some possible applications of this framework and algorithm. Okay, so just to review what we're going to be talking about today, there's a lot of discussion in quantum machine learning about what some people call variational algorithms, others call quantum neural networks. The basic idea is all the same. You have some input training data. This could be, some training set of, images and labels. It could be a cost function, whatever it may be. And in the near term, we have quantum computers, which aren't perfect, but they can perform certain things very well. And the idea behind these algorithms is that we construct circuits, which we know we can perform on these near-term quantum computers. And we parameterize these circuits by putting parameters on each of the gates. And this forms some sort of, parameterized quantum neural network, if you may. And through some iterative process, we take outputs from this quantum computer, feed those outputs into some classical computer. And the classical computer then, over time, will update the individual parameters in your quantum circuit. And the hope is that, in this iterative process, that you can, perform learning or minimize the cost function, whatever your goal may be. And this forms the basis for most of the variational algorithms or quantum neural networks that you see in the field. So what's the problem? Ooh. Okay, so problem one is that there's a couple challenges we face. The first problem is that we know that this can be a very challenging task. We know that if you do not have enough parameters often in your model, learning is virtually impossible. And you will often get stuck on the local minimum. Here is an example from a paper we did in the past. It's just a simple thing where we tried to learn D by D unitary matrices. And as a reminder, any D by D unitary matrix has D squared parameters. And you'll notice in this chart that when we, reached this threshold of around one times this d squared parameters, just enough parameters, the learning sort of becomes possible. Whenever you over parameterize, you can learn pretty rapidly. This is 1.1 d squared here, this purple line. But when you have less than d squared parameters, learning doesn't quite get achieved. And this example has been repeated by others, and it shows basically that, like, in general, when you construct something random or something, that's just from some ansatz, and you try to create some general thing that you try to learn, in many cases, it's often very, very difficult to perform the learning. And if you try with less parameters than is available, you can get stuck in local minima. Another challenge, which many of you may have heard of, is what are called barren plateaus or exponentially decaying gradients. The basic concept here is that as you increase the number of qubits, the gradients, the variance in the gradients of your parameters often decays exponentially. So this means that gradients will decay with the number of qubits to 0 exponentially fast. So if you have, 10 qubits, you'll have order 2 to the negative 10 value of your gradients, which is not exactly a great thing because, oftentimes when you use a quantum computer to measure gradients or to measure anything really, you often do it through sampling procedures. And if something decays exponentially fast, you also need exponentially many samples to measure it. And this can be a huge hindrance to any attempts to perform machine learning on a quantum computer. So I'm going to go and try to tackle a couple of these ideas with this new idea. Before I jump into any of what our work does and how it addresses these challenges, let's just talk about what our goal is here. So we're trying to perform what are called generative algorithms. These are algorithms that generate, given input samples, some outputs that are useful. And in the classical sense, you have some probability distribution which you sample from, you feed this into a generator, and the generator outputs samples from some output probability distribution. You can think of this input distribution as, like, in an example, you can think of this as some, index or number that you feed into a generator, and that generator then outputs images of dogs, for example. Like, let's say you want to generate new images of dogs. So that's an example in a classical world. In the quantum world, we no longer have probability distributions, but we have quantum states. And the idea here is that we feed in some quantum state in the input. It goes through a generator, and the generator outputs a quantum state, which is close to, ideally, some target quantum state. In the same way that we want our samples in the classical case to be close to the probability distribution of the target, in the quantum state, we want our output to be close to the state of the target. And this generator is basically this variational circuit that we discussed earlier, this so-called quantum neural network. Before we jump into how we can perform this, we have to first discuss how do we actually measure how close we are. Classically, this is a question of how close are two probability distributions. So you have, in the classical case, you have a generative probability distribution, the probability distribution which your generator creates, and you'll have your target probability distribution. And your question is, how do we compare these two to say how close we are? Your machine learning algorithm obviously has to minimize this distance. So this measure is very, very important. It's both a measure of progress, and it tells you how you can improve. A few of them I've shown here are commonly used in the classical case, and I'll try to make analogies to the quantum case with these distances. The first one is called the total variational distance. This measures basically the maximum difference in probability at any point in your support. The second one is KL divergence, or many of you have seen this. This is a more information theoretic measure. This is commonly used. It just has some issues associated with this. Can become unbounded often if you don't choose your supports wisely. And finally, the one I want to focus on actually is the Earth mover's distance. Let me see if I can close this. This Earth mover's distance is also called a Wasserstein metric. And And an important point I want to make is that these two distances here, the total variational distance and the KL divergence, these measure differences in probability distributions by comparing probabilities along the so-called y-axis. You can imagine, you have your support of your probability distribution, and you want to measure these, compare how much the probability distributions change over the actual values of the probability. Earth movers distances are a bit different. They compare distributions by so-called optimal transport measures. And the way this works is pretty simple. You can imagine your probability distributions as two lumps of sand. And the question is, how much do I have to move one lump of sand to make it overlap with the second lump of sand? And these can be done in various different norms. When you do it in the one norm, people often call it an earth mover's distance. And that's the norm we're going to pick for our work as well. Okay, so moving beyond, why would someone actually want to use this earth mover's distance in machine learning? The basic idea is that you want to, earth mover's distance compares intuitively across the spatial dimensions, whereas other distance metrics often compare across the actual output probability direction. And the reason we want to compare in the spatial direction is it often is far more stable to do this in this direction. The reason why is that you can imagine as your input space grows in dimension, the amount of overlap you'll have between two probability distributions often decays. To put in the quantum sense, as you increase the number of qubits, or as you increase the dimension of your Hilbert space, random quantum states have overlap that decays with the dimension of the space. So that means it would decay exponentially with the number of qubits. So any sort of measure like total variational distance or KL divergence has this feature that it can decay pretty rapidly as your dimension of your space grows. This is also an analogy, if you remember earlier, I talked about how we have exponentially decaying gradients in quantum mechanics. This is exactly related to that feature that, as the metrics we often choose to perform machine learning, they have this feature that as your dimension of your space grows, the actual amount you're measuring often decays exponentially or decays with the dimension. But an earth mover's distance doesn't have this issue. The earth mover's distance often decays, only decays often with the size of your space, your input space. Because you can imagine, like, in the classical case, if you have two Gaussians, as you increase the dimension, sure, you might have to, increase the, you might have to move the Wasserstein distance in one more dimension, but you won't have to move it exponentially more. So these earth movers distance, or these Wasserstein distances, often have the nice feature that they're much more stable in machine learning settings. Okay, so how do we define the earth mover's distance in quantum mechanics? Now, I know there's a lot of math on this slide, and I hate putting math on slides without a lot of explanation. So I will try to take my time here and go through it. I will say before I actually go through any math, this is not, we simplify this greatly in the exposition of our algorithm, but it is still good to go through this and just show how we actually calculate the Wasserstein distance. Okay, so there's the Wasserstein distance is a semi-definite program. There's a primal formulation and a dual formulation. In our algorithm, we use the dual formulation to perform machine learning, but I'll go through both of these, the primal and the dual. So in the primal formulation, the Wasserstein distance is basically calculated by forming couplings. The couplings are, the idea is that for each qubit, which are indexed by I, you want to form a state such that the sum of those xi's equal your state that you want to measure the Wasserstein distance over. Each of these states has trace of 0. And then once you form these xi's, the Wasserstein distance is basically the sum of the one norms of those states. I'll go through this. This might be a little confusing. I'll go through some properties of this that'll make this clear. But one way you can think of this is that in the computational basis, for any states that are diagonalizable in the computational basis, this recovers a sort of Hamming distance of the states. In the dual formulation, which we actually use in the algorithm itself, this is now formed in terms of some Hamiltonian. And we choose Hamiltonians, which what are called Lipschitz constants less than 1. This Lipschitz constant is is similar to the classical Lipschitz constant, which basically bounds the amount of change you can have by applying changes to 1 qubit. I'll have a definition for this later on, but the basic idea is just you want to find the maximum over all the Hamiltonians which have this Lipschitz constant less than or equal to 1. If you are, I don't want to dwell too much on the math here. If you are interested in talking about the math, feel free to stop me after as well, and we can go into much more detail. Again, this will all be simplified when we actually perform the algorithm.
I'm sorry to cut in here, Bobak, but I could just see in the participants list that we have a few students attending, and I'm not sure. Maybe you could just remind everyone what the classical Hamming distance is, because I think that's like a really good intuition to have when thinking about this.
Sure. Let me see if I can. That was actually my next slide. Okay.
Okay.
So the Hamming distance is basically, before I'll answer David's question in a second. This slide just shows a few properties that'll help you in understanding how this distance works. And the first one is this Hamming distance I mentioned. The Hamming distance is basically just the number of, like if you put in 2 states into the Hamming distance is the number of entries which differ between those 2 states. So for example, the Hamming distance between 0, 0, 0 and 0, 0, 1 is just 1 because it only differs in this third one. Similarly, I put a few more examples down here. This is a pretty useful thing to have. If you can imagine in quantum, like when you're actually doing quantum operations, this Hamming distance sort of implies that to get from one state to another, you need to, like let's say you have a Hamming distance of order n, you need order n local operations to get one state to the other. That's sort of an intuition that Hamming distance provides, and it's useful because it just basically encodes, how far a state is in terms of the number of operations you need to make. Other useful measures that we have with the Earth mover's distance is that if we take the partial traces of states for up to its kth subsystems, and then look at the individual distances over those kth subsystems, we have this superadditivity or locality. Another way to put this is that this bound is saturated when these 2 states are tensor products along the kth and the k+1 to nth subsystems. One thing I want to note is that if you have any unitarily invariant distance, things like inner product, things like relative entropy, things like trace distance, these properties will not be in general met. So this is one. These are all properties that the Earth mover's distance has, but more standard metrics in quantum mechanics does not meet. And finally, the other unique property is that if you have states, if you have probability distributions, which are basically just states in the canonical basis, so these are just states that are indexed by 0s and 1s, then the classical EM distance is recovered by our quantum Earth mover distance. Okay. Should I stop for questions, or?
I think we'll just go on until the end, and then we usually do questions at the end. But because you're willing to take questions throughout, maybe I can keep an eye on the Q&A button as well. Meanwhile, then I just interrupt.
Okay. Yeah, I'm just conscious that I'm going through this rapidly, so if there are questions, feel free.
Yeah, I think it's pretty clear. I think you're doing a good job.
Okay, thanks. Okay, so let's go on now. So how do we actually use this Earth mover's distance to perform learning? So the idea is that we have a generator state, which and we have a target state. And the idea is that we want to take this green state here that I've labeled as the generator state and move it towards this orange state, which is the target state. And notice this is the Earth mover's distance in its dual formulation. The basic idea is that we play a game between a generator and a discriminator. And the discriminator's goal is to perform this maximization. It wants to find the Hamiltonian that maximizes this formula here. And again, this formula is just simply the Earth mover's distance. The generator wants to find a state that minimizes the energy associated with trace of this thing here, this quantity here. So basically, the game goes as follows. The discriminator takes a turn, finds the Hamiltonian with Lipschitz constant less than or equal to 1 that maximizes this Earth mover's distance. And then the generator takes its turn and tries to minimize the expectation value with respect to the Hamiltonian the discriminator hands it. And over a series of iterations, this will produce ideally a state that is very close to the target. If you are familiar with Wasserstein generative adversarial networks in the classical literature, this is virtually the same mechanism that we're using here, except we just translate it all into the quantum setting. And as promised, just a quick description of the Lipschitz constant. If we have a Hamiltonian, which is the sum of a bunch of terms, and here this squiggly I just says which qubits each individual term of the Hamiltonian acts on, we can bound the Lipschitz constant by taking a maximization over all the qubits and finding the infinity norms of the sums of these individual Hamiltonians which act on that qubit. This is, I know this looks a little complex, but basically the simple idea is that you look over each qubit. For each term that acts on the qubit, you sum up those Hamiltonians and take the infinity norm. This is a very straightforward thing that can be done even on a classical computer if you have Hamiltonians which are structured in a simple way. And the structure we choose in our paper, but there are other structures, is that we look at up to order 2 polys. So we include in the discriminator into the sum all the order 1 and 2 polys. And then this whole process becomes very, very easy to calculate the Lipschitz constant on a classical computer. Because, you know, for an n qubit state, there's only order n squared polys, and you can easily calculate this Lipschitz constant. So then this whole process here can become performed very, very easily using a interplay between a classical and a quantum computer. Perhaps to explain how this whole thing works, I'll go over a simple toy model. So the goal of this toy model is to generate the GHZ state, which is just this state here that I've written in this target. We start at the 0, 0, 0 state. And if you notice with the circuit here, to generate the GHZ state, if you set this circuit's parameter to pi over 2, and then all of these to pi, then this circuit here will generate the GHZ state. So that's the goal here. We just want to find the right parameters to generate the GHZ state using this circuit. But the challenge, again, as you probably have expected, is that, you know, if you don't see any of these parameters and we don't know the target is the GHZ state, we're just simply handed the target, it's not quite obvious what to set these parameters for. So the goal here is we're given a target state and we also given a circuit, and we want to somehow, by performing measurements or whatever on this state, find the right parameters to then construct that target state. 2 ways you can do this is, you know, traditionally people have proposed this before in the past, where we try to minimize the fidelity between the GHZ state and your generated state. Now, this has an issue, as I mentioned earlier, that the gradients can decay exponentially. So with this simple toy model, we can actually write out the fidelity exactly. You'll notice that the only order 1 gradient term is this first term, which is this term associated with this first rotation. If we minimize just this term, we will not get the GHZ state. Note that minimizing this term will set this to pi or to 0, and you only get a 0, 0, 0 state or a 1, 1, 1, 1 state, and not the entangled state. All the other terms in this cost function are a product of signs. And again, this is where you see the exponentially decaying gradient, because the product of signs decays exponentially with the number of qubits. So if you're trying to, if you're trying to minimize this cost function and generate the GHZ state using the fidelity, you're going to face this issue of exponentially decaying gradients pretty quickly. And as you try to find the values of these gradients, or as you try to optimize these parameters, you're going to need exponentially many samples to actually perform this optimization. This issue, I just mentioned it here, this does not arise with the Earth mover's distance. One simple way of seeing that is that each of these gates can perform an order 1 improvement on the Earth mover's distance. If you think about it in terms of the Hamming distance, each of these states changes the values of a single bit. And since the Earth mover's distance is a measure sort of like Hamming distance, if you improve the state over a single bit, you get an order 1 improvement in the Hamming distance. So this feature that the gradients decay exponentially will not be seen with the Earth mover's distance. And here we actually performed experiments on many, many qubits to show that if you use fidelity, your success probability of learning decays to 0, as the number of qubits grows. But using the Earth mover's distance, no matter the size of the target GHZ state, you can always perform the learning and generate the target state. Okay. So the GHZ state was simply a toy model. It's, maybe an interesting state, but it's not exactly the most complex thing out there. And one would hope that you can do cooler and more complex things and more varied things with this quantum GAN that we've constructed. And here we do exactly that. We look at something a bit more complex. In the barren plateau research, or the research on exponentially decaying gradients, this was the circuit they used to show that you can have exponentially decaying gradients. And we said, okay, let's just take this circuit. We know it's a circuit that previously has been shown to have difficulties in learning situations. Let's see if we can learn it. But before we see if we can learn it, let's just see what the gradients look like. Again, so if we, similar to before, if you look at the norms of our gradient vectors and we increase the number of qubits, what we find is that with an inner product metric, something like fidelity or trace distance, the norms decay exponentially with the number of qubits. This is a log scale on the y-axis. However, the quantum GAN metric, the gradients remain constant. So again, as before with the toy model, we see the same phenomenon that if you try to do this learning with other more standard quantum metrics, you're going to fall into issues pretty quickly. But with something like Earth mover's distance, you can still produce improvements at any stage of the process. In the same scenario that I discussed earlier, this plot shows how fast you can perform learning. I believe this is for 8 qubits, the 8 qubit scenario. Basically, this shows 50 simulations all in light lines. The optimization is typically performed within 100 or 200 steps of optimization. Sometimes it takes longer, but in general, this quantum GAN can learn the target state within 100 or 200 or so steps of discriminator and generator trading off their optimization programs. Okay, that is the end of the main part of the talk. I just want to end by discussing some applications of this Earth mover's distance and this quantum GAN. Some things you can do with this: you can perform quantum circuit compression. Let's say you want to generate a state by first, embedding it in a smaller subspace and then seeing if that smaller subspace with some fidelity creates the same state. You can, obviously use this Earth mover's distance to see if the compressed state matches well with the actual state you want to have. Other cool ideas that I've seen in the literature you can use with GANs. You can create variational versions of the linear solvers, the HHL algorithm. The basic idea here is that, you you create a guess state, you guess the inverse state that you want to actually construct, and then you apply the matrix to that guess state, or to that, that state that you think is the inverse, and then you try to get that state as close as possible to the B. To put it in other ways, if you have AX equals B, A and B, you guess what X is, you apply A to that X, and then you try to get that AX state as close as possible to B. And that's another application of, quantum GANs. Other things which we've thought about, I should have probably gone into a little more detail here, but as I mentioned earlier, the Earth mover's distance is a good way of saying how many local operations away am I from one state to another. And this is a useful concept in error correction, because in error correcting codes, we often want to put states that are orthogonal to each other as far apart as each other as they can be. And the idea with the Earth mover's distance is that we can now quantify how far two states are in a distance, which basically says this is how many operations you have to apply to get one state to the other. And this could be very useful in constructing encoding states for error correction, or performing error correction better. Finally, another application we have thought of is you can use this for classical data generation. Let's say you want to create a very small circuit to generate MNIST images, or create natural language processing data. Perhaps you can learn the parameters of these small circuits to generate these states using our Earth mover GAN. Finally, I just want to thank the many people who have worked on this and helped us along the way. Our group is small, but we do work with many people, and there were a lot of people involved in this work, and some of them I've listed here, but just want to acknowledge their work as well. That's all for me. I guess I can field questions now, David.
Yeah, thanks a lot, Bobak. This was a really excellent talk. I see some people have started putting their questions into the Q&A button. Just to reiterate, that for anyone who wants to ask a question, just press the Q&A button and write something there. But meanwhile, I will promote Jordan to a panelist. So Jordan will ask a question, and then after Jordan, Sven will ask a question.
Okay.
Oh, hello, Bobak. Thanks for the interesting presentation. It was really very nice. So I was just wondering, in the general case, how would you provide the target state to your algorithm?
So I'll answer that two ways. I'll say first, the target state ideally is given by, it's given to you in a form which you can measure. In practice, the only thing we'll actually need is we'll only need the expectation values associated with the individual. So actually, let me share my screen again. This might make more sense. One sec. Sorry, 1 second. So the only thing we really need, let me go to full screen. We only need to know the expectations of the target state with respect to these individual HIs here. So if we know those, that's all we need to perform this algorithm. But in general, the target state you can think of as something that you're given either by another circuit, or either as a set of states that you can then perform these then you can perform these expected values on. Does that make sense?
I muted you, Jordan.
Oh, sorry. Yes. Yeah, I think this makes sense.
Okay, and then we had a question. We had a question from Sven.
Yes. So thanks for the talk. Unfortunately, I got somehow kicked out of the Zoom meeting when you tried to promote me to the panelist, so I didn't hear Jordan's question, and it might be very similar to mine. So I was wondering in what form. Yes. So in what form actually need the input state for this algorithm? So is rho provided to you as saying as some classical description of the density matrix, or do you somehow get rho of, do you get rho as a quantum state?
Yeah, so the basic idea is, you're given it to as a quantum state. In theory, the only thing we really need is the expectations of that state Hamiltonian terms, which you use in the discriminator. If you remember, the discriminator is the sum of a bunch of Hamiltonian terms, weighted sum of those. If we know those expected values of the target state with respect to those Hamiltonian terms, we can do the rest classically. But the idea here is more that we're given a quantum target. This quantum target can be some data that we store in QRAM, or it can be something that is given to us in another form. And we want to learn that quantum target in some sort of fashion. Going back to maybe if I could discuss one of the examples in more detail, it's like if you think of HHL, this application of HHL, the target state can be this, you have AX equals B, the target state can be the B. And then you want to find an X, or you want to guess an X such that when you multiply A to it, it gets close to that B. And that's one example of a target state you can get. Does that sort of help?
Seems like Sven is having some Wi-Fi difficulties. I can't really hear him, but I think your answer made sense. I had a question to ask you, Bobak. Sven, are you back? No.
I can hear you fine all the time. So yes, that answered my question well. Thanks.
Sure.
Okay, thanks. So I had a question about whether or not the Earth mover distance is always kind of a better metric to use than fidelity. So say that, I mean, yeah, I don't have a very, very good physical intuition yet for what the Earth mover distance is, but from what I understand, if you have a state 1, 1, 1, 1, 0, then that's in Earth mover distance very close to 1, 1, 1, 1, 1. But in fidelity, they're very different. But say that you had a state saying 0 plus 1 and then 0 minus 1. Would they be very different in Earth mover distance, or would they be the same?
Sorry, 0 plus 1, 0 minus 1.
Yeah, so just like the Pauli X basis.
Oh, I see. And you want to measure the distance between those two states? Yeah.
So here, I guess the fidelity measure is really good, right? Because you have a 0 and you have a 1, so they kind of look the same, but you know that they're the opposite of each other. So fidelity is a good measure. Does the Earth mover distance capture stuff like that, or?
So yeah, that point raises, they do different things, I would say. So one of the things with fidelity or inner product, if you have 0, 0, 0, 0, 0, 0, and then a 1 at the very end, and you measure the overlap with the all 0 state, the inner product is going to be 0. Those states are going to be orthogonal. They're going to be, at least in terms of using a fidelity or a trace distance or whatever, they're going to be as far apart as possible. But in quantum Earth movers distance, they're going to be only 1 unit distance away. 1 out of the total n units of distance away they can be. So they measure two very, very different ideas. Yeah, they're a bit different, but there are bounds between the two. So you can for example, if I'm not mistaken, the trace distance is, I think, at most 2 times the Earth mover's distance and at least 1 over n times the Earth mover's distance. Don't quote me on that, but
yeah, that kind of makes sense with the number of cubes. Okay.
Yeah, there are bounds like that. If you go to the original paper, I can, the one with Giacomo and all them, they have a lot of bounds there on relating it to other distances.
I bet they do, yeah.
But I'll say it this way too: if you converge, if you reduce trace distance or if you reduce Earth mover's distance, then you necessarily also will reduce the other distances down to 0.
Oh, so that was kind of what I was going for. So if you're reducing Earth mover distance, you will automatically reduce kind of unitary invariant distances as well.
If you converge to 0, yeah. I mean,
if you converge to 0.
Yeah.
Okay. So that's a really nice property, I guess, because, okay.
Yeah.
Okay.
I have another question as well.
Sure.
So in the toy model and the more advanced model that you showed, basically we're optimizing for these theta parameters that will give you the best or the closest to the target state. But the shape of the circuit or the actual nature of the circuit is predetermined, right? Do you have to know this beforehand? Is this something that's set in stone and doesn't change, or could this be something that changes with the qWGAN?
Yeah, so the generator, the circuit you have to pick yourself, or you have to take it from some ansatz that you know is good.
Right.
The basic idea is that this circuit is, different circuits will be good in different cases. Certain circuits are good for, generating certain types of data. Other circuits are good at generating other types of data. This circuit is handed to the qGAN.
Right.
And ideally, that circuit can recreate the target state.
Yeah, okay. But then if we go beyond toy models and we go to really, really large states in a full-fledged quantum computer, these can be quite tricky to come up with the actual right form of the circuit that is then to be optimized, right? I guess you could go and give it all the possible gates and it'll find something, but then it might be a useless, like you might be doing too many operations here.
Yeah, it's a general challenge in quantum machine learning that, some states can be really random, really hard to learn. The idea here, our hope with this algorithm is not to, say we can learn everything. Our hope is that if it is learnable, if, there exists some configuration which is good, this Earth mover GAN can help find that configuration better. That's the idea.
Yeah.
I do agree that in general, it can be very, very hard to learn these things. And the circuits that you need to construct obviously should be able to, learn well a given target.
Okay.
Okay, do we have any other questions? Yeah, I see a question here. Okay, we have a question from Shenghao. Shenghao, just a second.
Yeah, I had a question about your final discussion point about quantum error correction.
Sure.
I remember you mentioning that in error correction, we want two orthogonal states to be as far as possible from each other. But in your discussion with David, you also mentioned like if we have two orthogonal states, 0, 1, and 0, 0, their Earth mover distance is just 1. And so how does this fit into your discussion with about the error correction keeping orthogonal states as far as possible?
Oh, sorry, I should have been clear there. If you converge in the Earth mover's distance, you'll converge to in trace distance. But orthogonal states do not necessarily have Earth mover distance of 0. If you think of simple computational basis states like a 0, 0, 0, 0 and a 0, 0, 1 are orthogonal, but they have Hamming distance of 1.
Okay.
But the idea with the quantum error correction, sorry, I should have been clear, is that ideally you want to encode states into two different orthogonal states which are very far apart, and this very far apart in the Earth mover's distance is, in a sense, a term of how many local gates you have to apply to move one state to the other. And obviously, the application error correction then become clear if you think of it that way.
Okay, I see. Thank you.
Yep.
Okay, I think we probably coming towards the end of this. We've had many questions so far. So unless someone writes something just now, I think I'm gonna conclude this. So thanks a lot, Bobak, for coming and waking up so early and giving this presentation. Super interesting research, obviously.